Oh, that's definitely. Morning announcements, vital information for your everyday life. All right, stop. Okay. Let's see. We are chill. Done. Let me check one more again. This session is being live streamed to my YouTube channel. Let me get these gentlemen. There's one. And two. All right. The man. One more. Oh, almost missed him. Got him though. TJ. All right, I think we got everybody here. Let me see. 12. That is correct. All right. Let me share my screen. Start the broadcast. And optimize the video. All right. So we'll start off here. Come on. That's good like that. Okay. So welcome, gentlemen. 20 minutes before the start of class. I'm looking, I'm like, I only got 20 minutes. I know I don't have enough time for a full match, but I'm gonna try anyway. I did a match before that lasted 17 minutes. I was like, if I push hard, we can do it in 20 minutes. So going through the battle's going good. We have an advantage. I'm in the lead. We're in the lead. I look at the clock. Class starts in 5 minutes. I was like, damn. So I was being responsible adult. I was irresponsible because I knew I didn't have enough time to finish that match before class started. More than likely. But then I was responsible because I just abandoned the match. So when I get back on, they're gonna be mad. I'm gonna get all these strikes. I don't care. I mean, I need to be here whenever possible. Okay, so just a little random story. Let's see. What are we working on today? Oh, we're continuing chapter 2, right? Chapter 2, right? Yeah, it's no real announcements. Just as long as you're making your way through the assignments, let me kind of reiterate. So like, with the homework, right, you get unlimited attempts. So if you get it wrong, if you click similar question and you get it right, it'll give you credit for it. With the homework, with the quizzes and the exams, if you finish those assignments and you don't like the score, you can just take it again. And if you improve your score, the system is going to keep a record of your highest score, right? So with all assignments, we actually get unlimited attempts. It's just the quizzes and exams are a little bit different than the homework, but you still get unlimited attempts. So then also when it comes to the homework, right, keep in mind that at least 90% of the questions have an explanation attached to each question. So that's the reason why I use Pearson, because to me, it's the most user-friendly online management tool for like mathematics that I've experienced between some of the other platforms. Because of the viewing example, it gives an explanation like step by step. It gives you the same question with different numbers. And so like, with students in the past, what they would do is like, once they figure out the question, they would do it at least 2 more times. They would do every question at least 3 times. Well, at least the students that said that they did that, they did really well in the course, right? So I'm just passing it on. If that is not serving you, I know I had at least one student make use of my office hours. I did get a text. I just been irresponsible in that regards. I'll check it later. From one of you all. But yeah, make use of my office hours. Collaborate with your classmates and make use of the tutoring service. All right, the tutoring service is included in your tuition. You've already paid them, so you might as well get your money's worth out of them. As usual, if you have questions, feel free to unmute yourself. And let me see the goal for this week. Let me check one more time because I might be derivatives of natural log. Wait a minute. Oh, I almost skipped Monday. Oh, okay. Okay. So I definitely was about to do 2.4, and then I realized we haven't talked about 2.3. So let me backtrack and start with 2.3. Let me check one other thing real quick.
Can I ask you a question, Mr. Pfeiffer?
Yes, go ahead.
So just to clarify, I've been doing the work on my math lab. So we really have all semester to do the work, but if you do it late, it's just 10% off, right?
Hopefully I changed those to 5%. If I haven't, if you remind me at the end of class, I'll try to. Well, actually, I can't do it at the end of class. Just try to. If they still say 10%, just remind me at the end of the class, and maybe send me a text like, I don't know, just some random time.
Okay, I'll just shoot you an email. I just wanted to pop in. I have a meeting today to go to, so I was actually going to leave class early, but I'll shoot you an email regarding the late assignments.
Yeah, you don't have to announce something. Like, just, it's okay. Like, as long as you get your attendance, just kind of, because now everybody's like, well, if he's leaving, But I don't know that you want to miss stuff like this, even though it is recorded. It's not really a big deal, but but the main thing is, I do need to be reminded about that, because I do want those to be 5% instead of 10%. I'd rather them be 5%. If I haven't changed them already, I may have changed them already. But yeah, but the gist of what you were saying is correct. Let me okay. I know we did the derivative of E, so I think we need to do these two sections today. So we'll do the best we can as far as time. I'm so glad I went back because I almost skipped a section, and I definitely don't want to shortchange you guys. Okay, so and it's a short section. So we're continuing chapter 2 with we're going to start with section 2.3 today, derivatives of natural log functions, right? So last time I know that we talked about the derivative of the exponential function, right? Derivative of e to the x. And the thing with the derivative of e is it is its own derivative, right? So the derivative of e to the x is itself, right? And we explored some concepts and applications centered around that technique. So now we take it to the next step, right? If we explore the derivative of e to the x, then the next logical flow would be, okay, well, let's explore the derivative of natural log, because the natural log is the inverse of e to the x, right? So let's take a look at this. A few objectives: differentiate functions involving natural logarithms and solve applied problems involving natural logarithmic functions and their derivatives. Okay. So for any positive number x, d by dx of the natural log of x equals 1 over x. So the derivative of natural log is 1 over x. Okay, there's a little bit more to that, but we'll let it be for now. So for instance, in these example, this is pretty straightforward. Let's see, I got this. And I'll check attendance again in about 7 minutes, a little over 7 minutes for students that are coming late. Okay. Let's see. Okay, so we just said that the derivative of natural log is 1 over x. So then dy by dx of the first one should just be 5 over x. Okay. All right. All right, so let's let that be. I'm gonna copy this. No, copy. All right. All right, so for the second one, if we want to find the derivative of y with respect to x, for this first part, right, we have a product. All right, so we have to apply the product rule. All right, so just take a moment to yourself. Do you remember the product rule? The product rule goes first times the derivative of the second plus the second times the derivative of the first. Okay. All right. So we're saying the first, which is this guy. The derivative of natural log is 1 over x plus the second, which is natural log of x, times the derivative of the first is going to be 3x squared. And then that final term, the derivative of 4x is just 4. X cubed divided by x is x squared. Okay. We're going to leave that. Let me see. Plus 3x squared times the natural log of x plus 4. Okay. So I think I'm going to just go with that. And then part C looks like it's the quotient rule. And if you want it, you could always, like in this case, you can rewrite it as a product, right? So you could write it as x to the -2 times the natural log of x, and then just use the product rule. So you don't necessarily, in this one, you don't necessarily have to do the quotient rule, but I'm just going to showcase the quotient. So take a moment to yourself to see if you can remember the quotient rule. Hopefully, I don't know if it would be second nature by now, but hopefully on some level it's starting to sink in. So the quotient rule goes low D high minus high D low over low low, right? So the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square, all right? Okay. So dy by dx, the bottom is, the derivative of the top is this guy, minus, let me say low D high. The top, this guy. The derivative of the bottom is this guy, all over the bottom square. So it's going to be x to the fourth. Okay. Let's see. So that's x. It looks like we can factor out at least an x, right? We can factor out an x from all the terms. Let me see. Been a little bit not as lazy, isn't it? I just running out of space. So this guy turns that into an x. We can factor out this x and this remaining x. All right. And it's going to cancel. It's going to turn that from a 4 to a 3. Right. And so that x is going to be gone. Okay. So I'm just going to try to account for those changes. So for that, let me think about it. So then that means that there's a 1 here, right? Minus 2 natural log of x over x to the power 3. Okay. Again, I just kind of did it that way because I was kind of running short on space. But I think we have a typed version of that and a couple of sides. So we got 5 over x. Let me see. X squared plus 3x squared natural log of x plus 4. Yes. 1 minus 2 natural. Yeah, we got it. Right. And so here you can see a typed out of everything, right? And in that third one, you can see all the details that I skipped just because I was running short on space. Okay. Okay. See, so theorem 8. So the derivative, so we saw the derivative of natural log. Now, what if we're taking the log of some function? So then the derivative of the log of a function, the simplest way, the way I like to remember it is du over u, right? So the derivative of the function divided by the function, right? So yeah, that's the simplest way I can remember it. So du over u, right? Like kind of how it's expressed in the second one. So the derivative of the function divided by the function. Okay. So given these A, B, and C, and D, we actually differentiate. I don't think I'm gonna do all of them. I'll just do it until I fill up the space on the screen. I will at least do A. Okay. So if we have y equals the natural log of 3x, okay. So it's du over u. So then dy by dx. So the derivative of the function, the derivative of 3x is just 3 over 3x. The 3's cancel, and we're left with 1 over x. Okay. So I just basically said the derivative of the function divided by the function, and then I simplified. Let's try B. Another thing is I think like my disposition, I'm already in like weekend mode. So it's like, because I have classes kind of that go tonight, like after you guys, I have another class that goes, and we don't get out until like almost 9 o'clock. So then I sleep, and then when I wake up, I have like a class. So it's like all you guys are kind of jammed together in like a matter of 12 hours. So then after that 12 hours, I start my weekend. So then it's like, so I'm already kind of there. So I'm a little bit distracted. So you just have to bear with me. Okay. So with B, we have y equals the natural log of x squared minus 5. Okay. We are in chapter 2. I might be doing some grade updates. Maybe I might I haven't decided on like what topics, like it's going to be based on whatever's due at that time and whenever I decide to pull the grades. And again, whenever you see grade updates, it's really just a snapshot of where you are, you know, based on whatever was due. It's just a snapshot of where you were at that moment in time. It has no bearing on the final grade. The only grade that matters is the final grade at the end of the semester. All right. So, you know, as we kind of do these intermediate grade updates, it's just some feedback so you can have a sense of what I see on my end. Like, okay, I see you did this assignment. I didn't see that assignment, right? And so that if anything is out of order, you know, we can resolve it or whatever. But that you can anticipate something like that for like next week, possibly. It just depends. Okay, so the derivative of natural log, again, the way I remember it is du over u, right? So the derivative of y with respect to x. Hopefully you were thinking about it while I was kind of stalling a little bit. So the derivative of x squared minus 5, that derivative is what? I think I just said the answer is 2x divided by the function itself. And I think that's about all that we can do there. Like nothing simplifies or cancels or factors. I think that's about it there. Okay. So this isn't too terribly bad so far. Now, I will say that sometimes these examples do get a little bit extra. Like with those questions on Pearson, just do the best you can, right? Take advantage of the unlimited attempts. Don't hesitate to ask me or get help from somebody, right? If it's not me, then somebody that's knowledgeable. Just take a deep breath and do your best. But again, just take advantage of the unlimited attempts because some of those questions are kind of ridiculous. You could always do the ask my instructor and then I'll walk you through it. You might get credit for it. You might be able to use what I'm doing to answer the question. Sometimes that works. So, just do the best you can. ABC. All right. So if f of x, now we got the natural log of x, okay? So then f prime, so the derivative is du over u, but the derivative of natural log is what, 1 over x over the natural log of x? Yeah. So then we can write this as x natural log of x under 1. I'm thinking about that match before we started class. Like, so with those matches, it's a 5-on-5 battle royale. And like when we're picking our characters, it's a draft pick. So you have like one person chooses on one team, then 2 people on the other team chooses, and it alternates until everybody's chosen. And we ban characters. And so like one of my teammates banned the guy I was going to use, and I was pissed. I was like, damn it, man. I was going to use that person. I had just built their thing and I wanted to test it out in battle. So, and that knowing I'm already short on time. So then I was kind of talking smack. I was like, you should have banned the person I told you to. He was like, no speaking English. He said something like that. He was like, I don't speak English. And then I was like, oh, you don't speak English? How about I'm troll? Do you understand that? He was like, oh, you're gonna troll? And then he started speaking English. It was funny. It was a lot of fun. It was just really silly. He talked about he don't speak English. Then I said, I'm gonna troll. And he was like, oh, you're gonna troll? Now he's trying to talk smack. It was hilarious. Right. And I mean, we were winning. I got like the first kill, and like, we were doing well, but I looked at the clock. I had 5 minutes before the start of class. I was like, nope, gotta go. Like, he told you should have banned the other person, because I think I could have done it a little bit faster. Okay, so here's our f, right? So same deal. The derivative of natural log is du over u, right? So, shiesty, that's a lot. Okay, before I take this derivative, I'm going to rewrite it, right? So we could do the quotient rule, but I just don't want to do it right now. So I'm going to, since we're dividing by a monomial, we can distribute that 1 over x into the numerator, right? So x cubed divided by x can become x squared. And I'm going to write this second term as 4 times x to the negative 1. We're still taking the natural log of this, okay? So now, when I go to find my f prime, the derivative of the function is going to become 2x, what is that? Minus 4x to the minus 2, okay? Over is, let me see, minus 4x. That's du over u. So our u is x squared plus 4x to the minus 1. Now, I don't think it was the time. Oh, let me finish this one and now I'll look for people in Zoom. Since it wasn't given to us with like negative exponents, we probably should write them with positive exponents. So we can multiply by 1 in the form of Let me see, if that denominator is x squared, we can multiply by 1 in the form of x squared over x squared, and it should cancel out all the fractions. Okay. So then, let me see, if I distribute this guy here and here, let me see. What is that? That's going to be a 2x cubed. The x squares are going to cancel, so that's going to be minus 4 over, that's going to become x to the 4. Let me see, x to the 2, so plus 4x. We could factor out a 2, but that won't cancel anything. On bottom, we could factor out an x, but that won't cancel anything. So I think this is it. Okay, and we'll see the result in just a moment. Hopefully. So, you know, I kind of, we could have done, you know, quotient rule. I just didn't want to do it. So I rewrote that quotient, you know, as you saw, and then I calculated. Then I wrote it where the final result had positive powers. Okay. So the first one, let me see. 1 over x, 2 over x squared minus 5. Okay. I think we got the 1 over x natural log of x. 2. Yeah, I think that's good. Wait a minute. Yeah, we got it. We could factor out an x, but it doesn't cancel anything. And we could factor out a 2, so yeah, we got that. We got the same result. Okay. I feel like there should be questions, right? But I totally understand if there aren't any. And again, when it comes to like this content, you know, when we're having these live sessions or whatever, just absorb, just kind of try to let it be conversational and try to get the gist or the underlying theme or pattern or concept. Don't try to read too heavy into these. I feel like you really can't see it until you attempt it yourself, right? As like I know when I was working with the student in the tutoring, you know, I did something like I worked a problem, and then I was like, okay, now you try it, and he did it, and then I got stuck trying to follow his work. I was like, wait a minute, I can't see it, right? So I struggle to even follow other people's work. I just can't follow it, right? I can only see it when I do it myself, and then I match up the parts, right? Um, so I just say that to say, you know, try to let this be like conversational. Don't read too heavy into like the live session. Just try to let it be what it is, and then go back and attempt these examples like in a testing or proctored environment, right? So just try it yourself without the answers and see, can you generate the answers? If you get stuck, then you refer back to like, you know, this type text or whatever. Or even try these quick checks. Like start with the original question. Don't look at the answer. Try to answer them. Like make a little worksheet or whatever. Like cover up the answers and then see, can you answer it? And then, you know, that's a good way to learn. Like the more you can consistently get that correct in that kind of setting, then the better off you'll be. Okay. So then in example 3, in a psychological experiment, students were shown a set of nonsense syllables such as POK, RIZ, DEQ, and so on, and asked to recall them every minute thereafter. The percentage, R of T, who retained the syllables after T minutes was found to be given by this logarithmic learning model given here, as for T as it goes from 1 to 15 minutes. What percentage of students retain the syllables after 1 minute? So we let T be 1, we just plug in. And then find R prime of 2. So that's the rate of change of the retention per minute, right? So the derivative is the rate of change. So the rate of change of the percent of students, the retention per minute, right? The percentage of students, right? So the rate of change of the percentage of students per minute. Okay. All right, so for the first one, again, we're just plugging in T equals 1. Well, the natural log of 1 is 0, all right? So that's just going to be 80, all right? I'll just kind of make a quick note. You know, the natural log of 1 equals 0. So that means this term goes to 0. So then for part A, the result is 80. 80, whatever the units are, 80%. What percentage of students retain the syllables after 1 minute? 80%. Okay. Find R prime of 2. So we need the derivative. I really don't have the space, but I think I'm going to try to get it to work. So I'll write it here for right now. R prime, the derivative. So for this first term, the derivative of a constant, think about that for a constant is 0, right? So when we take the derivative of natural log, is 1 over t. So then ultimately our prime is going to be negative 27 over t. Can't write my t's today. Okay, so negative 27 over t. Okay, so then if that's r prime, so then r prime of 2, looks like it's negative 27 over 2, 13.5, negative 13.5. So the retention is dropping by 13.5% per minute. The percentage of students that retain the syllables is dropping by 13.5% per minute. Okay, that's interesting. Let me see, that makes sense. All right. Okay, let's see, how do we do? 80% and the negative 13.5. So the result indicates that 2 minutes after students have been shown the syllables, the percentage of them who remember the syllables is shrinking at a rate of 13.5% per minute. So after 2 minutes, then that's the rate of decrease. Okay. So that was the end of the derivatives of natural log. This is a summary. It's a quick summary, right? The derivative of natural log is 1 over x. And then whenever we take in the natural log of some function, the way I remember it is du over u. You might remember it as like f prime over f, right? Things like that. Let me make a copy of this available. I like to share the box. Let's get to the right folder. Yeah, because it's not called that anymore. Oh, also, I noticed with the tutoring session, the student brought to my attention I had the wrong office cell phone number. So I did update that cell phone number on the syllabus. I think I had like a 365. It was supposed to be 465. And everything else is the same. So it should work now. This is traditional calculus notes updated daily. Yes. I need to change that as well. Did we not do 2.2? Where's 2.2? Maybe I didn't share it. Okay. Let me export this. Let me see. So we just did 2.3. Maybe I just forgot to share 2.2 because we definitely did the derivatives of exponential. So let me go ahead and share it right now. Let me share to box. Yeah, let's export. Okay. Okay, so that was from last class. And then, so we're pretty good on time, right at about what we needed. So we'll go ahead and start in section 2.4. And this is about the same length. It's rather short as well. So that's a good thing. Okay. So hopefully we're all aboard and we're not all bored. I just try to throw a little bit of quirky stuff in there just so it's not so dry and drab and mundane. Chapter 2, we're continuing chapter 2 on exponential and log functions with section 2.4 applications, uninhibited and limited growth models. A few objectives: find functions that satisfy dp by dt, the derivative of p with respect to t equals kp, okay? And then solve application problems using exponential growth and limited growth models, okay? So we have this theorem 9, a function y equals f of x satisfies the equation dy by dx equals k times y, or f prime equals k times f, if and only if y equals ce to the kx, or f of x equals ce to the kx, right? So for some constant c. So this is basically exploring functions where when you take their derivative, the result is going to be a constant times the original function. Right, and that happens basically when we're working with the exponential growth model or the exponential function. Right? So that's all that this is referring to. Functions that when we take their derivative, the result is a constant times the original function. Okay. So find the general form of the function that satisfies this equation. Oh no, Oh no, I didn't want that showing. That's the answer. Yeah, I'm just gonna have to go with it now. So find the general form of a function that satisfies this equation. The derivative of a with respect to t equals 5 times a. So by theorem 9, it has to be of this form. Well, that's not the full answer, right? It has to take on this form. Let's see. The general form of a function that satisfies this equation. Oh, 5. Okay. So if it has to take on this form, and we go to find a prime of t, let me see. That's going to be c. The derivative of e is itself, e to the power of 5t times the derivative of that power, which is 5. And we want this to equal 5 times the original function, right? The original function being c e to 5t. So, darn it. Wait a minute. So something's missing. C e to 5t. Oh, okay. So we're trying to solve for c, right? So we have c times 5e to the, let me see. Wait a minute. Yeah, 5e to the 5t. So here, let me rewrite this. So we have 5c times e to the 5t equals 5 times the original 5c e to the 5t, right? At first I thought, no, they are the same. Oh, they're not the same. Yeah, no, they are. So let c be 1 or something? Let me think about it. Okay. Sorry. 5 times a. We want it so that when we take the derivative, it equals 5 times the original. The original being that. Let me give me a moment. Because it's kind of being a little bit circular and I know I'm missing something. Just give me a moment. Okay, so we're trying to solve for c. Say this is the original, right? When we take the derivative, is c e to the 5t times 5. C e to the 5t times 5, right? If we divide both sides by 5, we just get this. Oh, so I think this is the answer. So yeah, I think that is just the answer. So let me see. Yeah, that is just the answer. That's I was like, why is this like being circular? Because that is the answer. Because that's why it kind of threw me off because I'm used to trying to solve these, and I accidentally had the answer on the slide right here. Because if we take the derivative of this guy, it's going to be 5 times the original, right? So this is already the result. Let me see. But all it was a direct application of this theorem. So the derivative of some function equals k times some y, if and only if. Basically, that k, we put it in the power, right? So it was just a direct application of this theorem. So I think that's why I left it. Let's just try another one. Quick check, I'm going to leave that. And this is a little bit different. So this equation, dp by dt equals kp, or p prime equals k times p of t, is the basic model of uninhibited or unrestrained population growth, whether the population is comprised of humans, bacteria in a culture, or dollars invested with interest compounded continuously. So then P of t equals C e to the kt, or P of t equals P naught e to the kt, where C is the initial population, P naught, and T is time. Yeah, that's fine. Okay. So suppose that an amount P naught in dollars is invested into a savings account where the interest compounded continuously at 7% per year. That is, the balance grows at a rate. That's the rate of growth. Okay. So find a function that satisfies the equation and write it in terms of P naught and 0.7. Okay. So if it's what is it called? Continuous compound interest. Let me see, P naught. So then P of T should take on the form. Is it 0.07 times E? Let me think about it. No. No. P naught, whatever the initial deposit is, times E to the power of 0.07 times T. All right. So, and then we just need to confirm that this is a function where when we take the derivative, we get 0.07 times the original function, right? So the derivative here, this is just a constant, so it kind of remains in front. The derivative of E is itself. Then we got to say times the derivative of the power, so it's going to be times 0.7, the 0.07. So now we're going to have 0.07 times the original function, which is our desired result, okay? It's a little bit circular, but, you know, let me do it like this. Okay. Let's see. Suppose that $10,000 is invested. What is the balance after 1 year? So then P naught is 10,000, and the time is 1 year. So then we just plug that in. We will use our calculator. Let's see. Calculator is here. Okay. And let's reload and refresh. Come on. Okay. Okay, so we said what, 10,000, 1, 2, 3, times E to the power of 0.07 times 1. I'll just go ahead and put times 1. And we get 725.08. 10,000, 725.08. So after a year, it's earned $700. What's the rate? 7%? 7% is a decent rate. That's actually pretty good. If 10,000 is invested, how fast is the balance growing after 1 year? So that's the rate of change after 1 year. So we just said that the derivative is going to be the 0.07 times the original function. So then dp by dt is going to be 0.07 times that result. 10,725.08. So we're just going to say the result times 0.07. Yeah, and that makes sense, right? Wait a minute. I guess that's the rate of growth after a year. $725.08. So the rate of growth is like a $7.50 per year. $0.76 per year. Yeah, running out of space. Best that we can. Okay. Let's get rid of this. That makes me a little bit nervous. I was anticipating it to be 725.08, but let's just go with it. All right, let's go with it and see what happens. So for A, P naught E to the 0.07 T, okay. We got 10,725.08, okay. 750.76. So at 1 year, the balance is growing at a rate of about 750.76 per year. That's exactly what we got. Okay. All right, let's try another one. The world population was approximately a little over $6 billion at the beginning of 2000. It has been estimated the population has grown exponentially at this rate, or about 1.6% per year. So the rate of growth of the population is 0.016 times P, where T is the time in years after 2000, okay? So find a function that satisfies the equation. Assume that P naught is this and K is this. Let me see. It should take on the form So the population should take on the form P naught times E to the power of K, which is the 0.016 times T. Okay. Yeah, because if we take the derivative of that, it gives us this. All right. So then it says, let me see. So then our P of T, if our P naught, so the starting population is 6.04 times E to the power of 0.016 T. I think this is a function. Yeah, I think this is okay. Okay. So this is really PERT, like from college algebra. PERT for continuous compound interest. So you have your initial amount times E to the power of RT. That's really all that I did here. And then I went back and checked, like by doing a quick derivative to make sure that it matches. And so like this previous slide, again, we're looking for a function such that when we take the derivative, we get this number times the original function. All right. So if you want to check that it's correct, you take the derivative here, and it should be that number times the original function, right? And it should work out. Okay. Estimate the world population at the beginning of 2020. So that's 20 years later. So now that we have this function, we let T be 20. Okay. So then I'll do 6.04 times E to the power of 0.016 times 20. Okay. Uh, 8 point, we'll say 3179. I think that's billion people. Okay. And then find the rate of change of the population at the beginning of 2020. Okay, so basically P prime of 20, right? So then P prime should be that number times the original. So then P prime of 20, let me see, the 0.016 times the original. Or actually, we can just say that number times the number we just found, like we did in the previous example. And I'll say it's approximate since we're rounding. So then in my calculator, I'm just going to say that answer times 0.016. So if that's billion, that's like, I'm just going to say, so it's grown by 1331 billion people per year. I think this is good. Paste. Okay. So for A, I think these are okay. 6.04 E to the 0.16. We got 8.3179 for B, 8.3179, and then for C, 0.11331, right? Billion per year. Okay. So the rate of growth of the population at the beginning of 2020 is roughly about 133 million people per year. All right, that's exactly what we got. Okay. Man, we are like, well, we got 10, moving a little bit quicker than I anticipated. Models of limited growth. I can't get my words up today. The logistic equation given where K is positive and L is positive, is one model for population growth in which there are factors presenting the population from exceeding some limiting value L, perhaps a limitation of food, living space, or other natural resources, right? So this is the logistic growth model, right? The other one, I think, grew exponentially, like unbounded. This one initially is going to grow exponentially, and then it's going to finish logistically. So it's going to start off growing rapidly, and then it's going to kind of like taper off, right? So that's the logistic growth. But it kind of makes like a weird sideways S kind of shape, right? Like this, right? Notice that initially it starts off growing exponentially along here, and then because of some limiting factor, it finishes in a logistic form, like a log function, right? So it starts off exponential, and then it finishes logarithmic in nature. That's just the way this behaves. We're just going to be using this function to answer our question. Let me see. So spread by skin-to-skin contact or via shared towels or clothing, methicillin resistant Staphylococcus. That's the best I'm going to do. MRSA. I'm gonna leave it at that. MRSA can easily spread a staph infection. Oh, I remember this. Staphylococcus aureus can easily spread a staph infection throughout a university. Left unchecked, the number of cases of MRSA on a university campus 2 weeks after the first cases occurs can be modeled by this guy here. I don't know if they do. I'm assuming they still have you guys take those. Like you have to have those shots to live on campus or something like that. I think we had to do that when I was a student there. Yeah. Okay, so we're given this model. Find the number of infected students after 3 weeks. Let me see something. Left unchecked, the number of cases of MRSA on a university campus T weeks, so T is based on weeks, after the first case can be modeled by this, okay? Find the number of infected students after 3 weeks, 40 weeks, and 80 weeks. So basically let T be 3, 40, and 80. We just plug those in and we get answers. Find the rate at which the disease is spreading after 20 weeks. So to find the rate, we're going to have to take the derivative. Looks like let's see. I'm going to go ahead. Let me see. I'm going to try it here. I'm going to use the quotient rule. Let's put in n prime of t. The bottom, which is this. Wait a minute. Yeah. 62.200 e to the negative 0.092 t. Oh, that's jammed. I need to give myself some space. The bottom times the derivative. Oh, the derivative of the top is 0, so we can get rid of all of that. Okay. So if we said the bottom times the derivative of the top minus the top, 568.803 times the derivative of the bottom. The derivative of 1 is 0, and the derivative of that guy is going to be that k times that. Okay. Let me do it here. It's negative 568.803. That derivative, this negative 92 comes down. Let me actually write it a little bit different. So when we go to take that derivative, e is its own derivative, so we're going to have 62.2 e to the negative 0.092 t. And then we have to say times the derivative of the power, which is going to be this negative 0.092. Okay. Okay. We said the bottom times the derivative of the top. That was gone. And then we said minus the top times the derivative of the bottom. Oh, then we got to say over the bottom squared. Is there one? Can we factor anything? Okay, this is getting a little bit extra. And I need to just give myself some space and stop trying to jam it in here. But it's really divided by 1 plus the 62.2 e to the negative 92 t, all of that squared, right? So I'm going to use it as a reference. I know it's jammed. But then all we need to do is let T be 20, or actually 20 weeks. We didn't do 20 weeks. Yeah. So can my calculator do derivatives? I should just write it out. Like part of it is I'm being lazy and not giving myself space. And so I know that's making it worse. Find the rate at which the disease is spreading after 20 weeks. I think we got it. Like I'll use some reference and we'll get it to work. And we'll check that one in just a moment. Explain why an uninhibited growth model is inappropriate, but a logistic growth equation is appropriate for this situation. Then use a calculator to graph the equation. Okay. An uninhibited growth model is inappropriate because it's not going to grow indefinitely. You're going to have limiting factors because you're on a campus. So it's either like limited to like the campus size or the population size, or maybe, it doesn't spread that way. Like it might start that way initially, but because students are like vaccinated, then it'll deter it, right? So I think we answered C. And then what I'm gonna do for the first couple of questions, I'm just gonna type the original here. Now, okay. Let me think. Give me a moment. Minimum solver in derivative. I think we can do derivative. Let me try the derivative. Let me see if we have like x squared, and we want to say the first derivative. I got to figure out the syntax. Oh, okay. With regards to x, and we want the first derivative. It should be 2x, right? Okay, let me try this. If I get rid of this. Oh. If I say 0? No. The first derivative, it should be 2x. Okay, what if I do this? Because it looks like the calculator can take the derivative. If it can, we can actually use it. But I got to look at the syntax. I want the first derivative of, where is it? Of x squared with regards to x. Turn. Okay, let me try one other thing. X squared, the first derivative with regards to x. Okay, let me look this up real quick. What is this? CI 83 plus. Oh, let me just look it up real quick. TI 83 plus. Why? Oh, to obtain the first derivative. Okay. Oh, function. What does that mean? Okay. F of x, press Command 8 to display interim or expression. Type in the remaining items. Hopefully it takes me straight there. Define a function derivative. Derivative, nth derivative to obtain second derivative. Okay, let me see. It says compute f prime from the home screen. Type the remaining items. What is the a? Oh, f prime of a. Okay. So you're taking the derivative of f with respect to x and evaluate it at a. Okay, I get it now. Okay, so we can do it. So let me do my trial again. So the derivative of x squared with respect to x evaluated at x should give us 2x. Darn it. Come on, I know you can do it. Let me see if I go here. I'll put x squared here. And variables. 0. Yeah, I gotta tinker with that to figure out how to get it to work. Let me see. What if I put? Yeah, that's not working. Or I'm missing something. In derivative f of x, x a. If derivative enter y1, y2 an expression for f of x, type in the remaining items and press enter. Set y2 equal to obtain the first derivative. Set y3 equal to the derivative to obtain the second derivative. Is obtained by pressing math 8. Compute the slope. Man. Okay, we still might be able to use it because I think what it is trying to do is evaluate it at a number. So like we know the derivative should be 2x. So then like what if x were 2? Let's go back and let's do like, let me try x to the power 3 comma x, and that would be 3x squared, and let's let x be 2. Evaluate it when x is 2. So there's going to be 12. Okay. So then what if we let this be x? Okay. All right, so it's trying to evaluate it at a number, right? That last one is trying to evaluate it at a number, 3x squared. Yeah. Okay. So we can use it to evaluate the derivative, which I think this question is actually asking. Now I know if I was working on a TI-89 plus or one of the TI-89s, it'll actually spit out the function, but I don't think this one is going to spit out the function for me. Find a rate at which a disease is spreading after 20 weeks. So we can have our function, and then we take the derivative and evaluate it when t is 20. So we can actually do that in the calculator, right? So that's why I took the time to do that. Let's see if we can do it, right? So if we, and this will be it because we kind of need to get going. If I go to my y equals, and I'm gonna just type in the original, we got this 568.803 divided by the denominator is 1 plus 62.2 times e to the power of a negative 0.092 t, and instead of t, I'm just putting an x. Okay, close off that power and close off the denominator. Hopefully I typed everything in properly. E to the negative. Okay. All right, so then what I'm gonna do, I hit math number 8 for the derivative. And I'm gonna go to variables and call on that function I just typed in. I wanna take the derivative of that function with respect to x, and I wanna evaluate it when x is 20. Okay. So I think that's the result, but before I do that one, let's answer the first part. Find the number of infected students after 3, 40, and 80 weeks. So we can actually do that here as well. If I go to variables, nope, clear. If I go to variables and y variables, number 1. So I want to evaluate this function when x was what, 3? We get this result. And then I want to evaluate this function when x is 40. We get this result. And I want to evaluate this when x is 80. We get this result. Okay. Then I want to pull up that derivative that we had when it was evaluated at 20, right? Find the rate at which the disease is spreading after 20 weeks. Okay, okay. We get this result. Oh, we can't see. Okay, I think we got all the results there. Okay, so I just answered A and B in the calculator. Let's see how do we do. 11.8 is correct. So about 12 students, 8/10 of a student. Oh my goodness. Oh no. 221.42. That's okay. It's a little different, which is approximately 222 students, and then approximately 547 students. Right. So we got those results. And then for the derivative, again, for those three, we just plug it into the original function. Now, here's a type version of it all worked out. I should have given myself a blank page to work that. I was just trying to rush a little bit. And so we ended up doing it in the calculator. So the rate of change after 20 weeks, they got 4.368. 4.368. Learn something new every day. All right. I think that was my first time doing derivative on the 83 plus. I've done it on the TI-89. I haven't found a TI-89 emulator, so that's the only reason I'm not showing it. But I always knew that this one could do it, and it can evaluate the derivative, but it doesn't spit out the function. So I was like, okay, well, we can use it for this question. So we got it. All right, look at God. All right, look at God. Okay. And we're pretty much at the end of this section, right? Okay. Okay, and then unrestricted growth is inappropriate for modeling the situation because as more students become infected, fewer are left to be newly infected. The logistic growth equation displays the rapid spread of the disease initially, as well as the slower growth in later weeks when there are fewer students left to be newly infected. Okay, well, that's a little bit different than what I said, but that's okay, right? And so this is how the function behaves. It starts off exponentially, and then it finishes logistically. Okay. All right, so we are out of time. Again, I feel like there should be questions. Let me kind of pause for a moment for questions. Go ahead and send a copy of this to Box. Okay. So you definitely have your work cut out for you. So again, my intent in the construction of all of this, I'm really just trying to expose you guys. I'm not trying to be rigorous. I'm not trying to be super hard. I do acknowledge that some of those questions on Pearson are a little bit ridiculous. So my way of addressing that is giving you guys unlimited attempts and a minimal late penalty. I do have to go to another class like that starts pretty much now. If I can remember, when I get out of that class about 9 o'clock. If not tonight, just over the next couple of days, if I can remember, if I haven't done it already, I'll change the late penalty from 10% to 5%. Okay. Are there any other burning questions before we go our separate ways? Going once, going twice. Okay. So again, you do have your work cut out for you. You definitely want to either collaborate, like do what you can on your own, collaborate, or link up with the tutors, or use my office hours. So one of those sources, something should click, but you got to push, and also take advantage of the unlimited attempts. If you just keep going until you get the score, you will get there, right? You'll get it. It's really just sitting there waiting for you to take it. Okay, so if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, have a great weekend, gentlemen, and we'll meet back on Monday, same time, same place. Take care. Peace. Okay. It was a little intense. It's a little bit bulky on my end, but we got through it. All right, guys. So I'm here if you have questions. Let me check the chat. I totally missed somebody. Yeah. I'm glad these guys hang around. Let me update my attendance. At least give them credit for it because I think I was supposed to check it and I just didn't. Let me see. Housey. Ford. I just forgot about these guys. That is not their fault. Scott. It's a student. And chat. Kai. Who is Kai? All right, so gentlemen, I know I just let some gentlemen in. I'm just letting you know that I gave you attendance credit because I don't even know that I checked it at the 15-minute mark. I meant to, and I think I got distracted. So If you're just getting into the call, you got your attendance credit, and you're gonna have to use like the recording for today. Yeah, but yeah, I'm going to give you credit for attendance, so you don't have to worry about that. Okay, Jim. Mark is absent. All right, gentlemen, have a good weekend. I don't see a Kai. I'm not sure who Kai is. All right, gentlemen.